Welcome to Orbital Dynamics, Part 60. This part is based on the books Orbital Mechanics for Engineering Students and Orbital Mechanics Theory and Applications. Keplerian orbits can be described in closed-form equations like the ones we developed for the two-body problem. Here's one that describes gravitational acceleration. This equation and others like them are based on the assumption that there are only two objects in space and that their gravitational fields are spherically symmetric. They also assume that one body is massive and the other is relatively small. Any effect that causes motion to deviate from a Keplerian trajectory is called a perturbation. We add a term p to account for perturbations. Common perturbations include a non-spherical central body, gravitational interactions with celestial objects like the moon and sun, solar radiation pressure, and atmospheric drag. Here are the relative magnitudes of all these effects. Earth oblateness affects orbits the most, lunar and solar gravity to a lesser extent, solar radiation even less. Atmospheric drag at an altitude of about 100 kilometers is large enough to deorbit a satellite, but the effect decreases rapidly with altitude and becomes negligible above 1,000 kilometers. There are three practical methods for accounting for these effects. One is to update the 6 classical Keplerian orbit elements on a regular basis based on celestial measurements. Here we're essentially ignoring the perturbations and updating predictions based on observations. 2 is to use an expanded set of orbital elements. This improves the predictions. 3 is to use numerical integration to propagate the predicted motion of a satellite. This is another mathematical method that improves the predictions. The GPS system uses the first techniques. Orbital elements are updated daily. The Russian GLONASS system uses numerical integration. The bulge of the equator causes the largest perturbation. Because there's more mass at the equator, when a satellite in an inclined orbit is north, the satellite experiences an extra pull downward toward the south. Likewise, when the satellite is south, there's an extra pull to the north. We talked about the oblate spheroid Earth in section 44. Imagine that this is a cross-section of the Earth. The oblateness here is highly exaggerated. If you're at the pole, the force of gravity is straight down. The same is true at the equator. If you're between the equator and the pole, you'd think that gravity would pull you toward the center. It doesn't. Gravity pulls you to the center of mass. Between the equator and the pole, the center of mass is offset. This creates a torque on the orbit plane, causing it to rotate west. If the inclination is greater than 90 degrees, then the extra pull is still south when the satellite is north and north when the satellite is south. But here the torque is in the reverse direction, east. The effect causes a shift in the right ascension of the ascending node. For high-altitude satellites, this effect is minimal. In those cases, the Earth is more like a point mass. This is the equation for the motion of a small satellite orbiting a large body with the term p added to account for perturbations. The vector p is the net perturbative acceleration from all sources other than the spherically symmetric gravitational attraction between the two bodies. A equals mu over r squared accounts for the acceleration. Let's use this coordinate system to define a point P some distance away from a spherical central body. The location of P is defined by the angles theta and phi and the length of the position vector r. These are polar coordinates in 3 dimensions. Let's assume that the gravitational field is rotationally symmetric. It then doesn't depend on the azimuth angle theta. If a satellite's orbit is not synchronized with the Earth's spin, then this is a valid assumption. Any rotational asymmetries would cancel out. The exception would be a geosynchronous orbit, which we'll talk about later. The polar coordinates for a point in 3-dimensional space would be r, theta, and phi. If we can ignore theta, then the polar coordinates are r and phi. They're 2-dimensional. The rotational symmetric perturbation phi at r little phi is given by this infinite series where j sub k are the zonal harmonics of the planet, big R is the equatorial radius, and p sub k are Legendre polynomials. Zonal harmonics are dimensionless numbers that are inferred from observations of satellite motions around a central body. They're unique to a specific central body. Here are the first 6 for the Earth. J1 equals 0. The summation above could have started at 2 and usually does. J2 dominates. The other harmonics are 3 orders of magnitude smaller than J2. The equation P sub k is a Legendre polynomial and is obtained by this formula derived by Olinde Rodriguez. P sub 2 of x equals this, which equals 1/2 3x squared minus 1. Since J2 dominates, a good approximation for perturbation simplifies to this. Here's the formula for a period of a satellite. The mean velocity in radians is 2 pi over the period t. That equals 1 over the square root of a cubed over gm. We can simplify this fraction. The gravitational parameter is g times m, so the mean velocity can be expressed as the square root of mu over a cubed. The equatorial bulge has an effect on the mean velocity. This equation assumes a spherical Earth with uniform density. Here's the equation for mean velocity that takes into account perturbations caused by the Earth's bulge. The first perturbation caused by the Earth's bulge, or the J2 effect, is a shift in the mean velocity, which translates into a shift in the orbital period. The term p is a semilattice rectum. It equals a times 1 minus e squared. If the orbit is circular, e will equal 0. P then would equal a, the semi-major axis. That simplifies this equation. Let's compute an actual shift in period. First, we'll define the constants. G is a gravitational constant. This is the mass of the Earth. Mu is the gravitational parameter, and is g times m. Here are the values for g and m. So for the Earth, this is the gravitational parameter mu. This is the mean orbital velocity for a circular Earth. With a circular orbit, the velocity is constant. Let's put the satellite at an altitude of 100 kilometers. I picked this low altitude because the perturbations are more pronounced. Here's the radius of the Earth at the equator. A, the semi-major axis, is Earth radius plus the altitude. Now we can plug in values for the mean orbital velocity. Here's what that comes out to. Now we'll derive the corrected mean orbital velocity. Let's take this a bit at a time. Let's focus on the fraction j2 times r squared over a squared. For this, we'll need a value of j2. This is the value for the Earth. Here we plug in values, and here's what that comes out to. Now let's focus on 3/2 sine squared I. For this, we need to pick an inclination. Let's use 55 degrees. You don't get the most perturbation at 55 degrees, but you get enough to see an effect. The equation becomes 3/2 sine 55 degrees squared. Here we've computed the sine 55 degrees, and here's what that equals. Now we can plug in those values to our equations for the corrected mean orbital motion. If we do the math for the terms in the brackets, it results in this. This is the uncorrected mean orbital motion times 0.99999. That's 5 nines. That's a very slight correction. That results in this. The difference is relatively small. Here's the difference in degrees. That equates to 0.06 degrees per day. Over a year, that's 22.4 degrees. What would this look like over a range of inclinations and altitudes? The two variables are the inclination I and the semi-major axis A. Here are the velocity shifts plotted over the range of inclinations from 0 to 180 degrees. The x-axis is the inclination. The y-axis is the degree shift. And the data series are the altitudes from 100 kilometers to 10,000 kilometers. They're depicted as different colored lines. The effects are most pronounced at lower altitudes, as you can see in the burgundy line that corresponds to 100 kilometers. At 10,000 kilometers, the effect is minimal. That's because as the satellite gets farther away, the Earth appears more like a point mass. Now consider the range of inclinations. The effects are most extreme at equatorial orbits, close to 0 and 180 degrees. There is no effect at 2 points on the graph. If 3/2 sine squared I equals 1, then the correction term in the brackets equals 1. The average velocity equals the uncorrected average velocity. We can multiply both sides by 2/3. We can then take the square root of both sides of the equation. I then equals the arc sine of the square root of 2/3, and I thus equals 54.7 and 125.3 degrees. At these inclinations, there's no perturbation of the satellite's velocity. Here's the satellite at 100 kilometers altitude. This animation starts with the satellite at the equator, at the ascending node. I grayed out Earth features. Subsequent animations run at a rate of 1 frame per rev or per day. At that rate, the spinning Earth is distracting. Notice how the stars in the background are fixed. These animations are in the stellar inertial frame of reference. The time step in this animation is 92.56 minutes. That's why it looks like the satellite's not moving. If you look at the time in the lower left-hand corner, you'll see the time is advancing. The time step of this animation is set to the period of this orbit, according to the classic Newtonian two-body equations. The time step here is the same 92.5 minutes as before, but this time we're using the J2 correction. Notice that the orbit plane precesses. Ignore that for the moment. We'll talk about that next. For now, look at how the satellite drifts off the equator. That means the orbital period is longer than 92.56 minutes. This is caused by the perturbation caused by the bulge of the Earth's equator. The corrected orbital period is 92.28 seconds. I'm sorry, that's minutes. Here's the equation for the shift in right ascension. We can simplify this equation for a circular orbit by setting p equal to a. Here's the new equation. I'm going to compute the RAN shift for a 55-degree inclination at an altitude of 100 kilometers. Here's the formula. We did this computation before. We also computed the mean velocity. The cosine of 55 degrees is this. We can plug in the known values, and if we do all those multiplications, it results in minus 1.09 times 10 to the minus 6 radians of RAN shift per second. That's 5.4 degrees per sidereal day. That's a significant shift in right ascension. You'll recall that a mean sidereal day is slightly less than a solar day, and it averages 86,164 seconds. The graph for the shift in right ascension looks like this. At 90 degrees of inclination, there is no shift. That's a polar orbit. The shift is more pronounced at lower altitudes and at equatorial orbits. At 100 kilometers, at a 100-kilometer equatorial orbit, the shift is almost 10 degrees per day. Here's what a 28.5 degree inclination looks like with no J2 perturbation. This uses Newtonian two-body math. The orbit planes stay fixed in inertial space. That means they don't move relative to the stars. The time step in this animation is 1 hour, and this is 10 days worth of orbits. That's why the satellites pop in and out here and there. Here's a simulation that takes into account the J2 effect. The satellite altitudes are 100 kilometers for the light blue, 500 for the yellow, and 1,000 for the magenta. You'll notice that the orbit planes precess westward, and the lower altitude orbit precesses at a faster rate. That's what our formula predicted. Here's satellites with inclinations that are 90 degrees off. Notice that one precesses to the east and the other to the west. And here I'm showing various inclinations. Notice that the 90-degree inclination shown in black doesn't precess. Notice, too, that the orbital periods are not the same for all these orbits. The blue satellite stays on the equator because I set the animation step to its period. The rest drift. The equatorial orbit is shown in magenta, and it precesses faster than all the other orbits, especially the black polar orbit, which doesn't precess at all. This shows the rate of precession of two equatorial orbits. The RAN moves faster to the east in the less inclined magenta orbit and slower in the higher inclination light blue orbit. Remember that the RAN is the crossing point between the ascending part of the orbit and the equator. That point is called the ascending node. This last equation characterizes a precession of the argument of perigee. This only occurs within a eccentric orbit. In a circular orbit, there is no perigee, hence no shift. Let's assume an orbit that looks like this. The semi-major axis is 8,500 kilometers, and the eccentricity is 0.2. This is much simpler if we assume an inclination of 90 degrees. That keeps the RAN stable, so we can see the full effect of the shift in the argument of perigee. P, the semilattice rectum, is 1 times 1 minus e squared. Here we plug in values, which results in 8.16 times 10 to the 6th meters. If we plug in all the known values, the mean orbital velocity is 8.05 times 10 to the minus 4th radians per second. The shift in RAN is 0, as we said, and the shift in the argument of perigee is 1.97 degrees per day. Here's what the shift in the argument of perigee looks like at various altitudes. Notice that the effect diminishes at higher altitudes. At 500 nautical miles of altitude, an orbit that's inclined 30 degrees will experience a shift of about 10 degrees per day. That's a total revolution about every 36 days. With this equation of 2 minus 5 halves sine squared I equals 0, the shift will be 0. That's then true for I equals 63.435 degrees and I equal to 116.565 degrees. Here's what the shift in argument of perigee looks like animated. The argument of perigee starts at the equator and then it heads southward. The atmosphere will cause an orbiting satellite to lose energy. It will ultimately spiral down to the surface of the Earth. The drag force on a satellite is expressed with this equation. C sub d is the drag coefficient. A is the cross-sectional area of the satellite, rho is the atmospheric density, and v is the satellite's velocity. If this is the velocity vector, and if this is the surface that is normal to the velocity vector, then the area of the surface would be the cross-sectional then the area of this surface would be the cross-sectional area. If this is the surface of the Earth, and if this is a column of air, then the atmospheric density would depend on the altitude. You know this from traveling at high altitude. The air is thinner, there's less oxygen, and if you've been living near sea level, it takes time to acclimate. At higher altitudes, the drag will be less. As the satellite loses energy, it will lose altitude. At the same time, the atmospheric density will increase, thus increasing the drag. Atmospheric density can be expressed by this equation. Rho sub SL is the density at sea level. Little h is the altitude, big H is the atmosphere's scale height of about 8 kilometers. The drag coefficient is determined with this equation. If you look closely, it's another form of the drag equation. The coefficient of drag is determined through empirical tests where drag force, atmospheric density, and cross-sectional area can be measured. Once measured and determined, the drag coefficient can then be used in the drag equation. The change in energy is 2 pi r times the drag d. Here's a plot produced by the Australian Space Academy. This shows a typical orbit degradation curve. The predicted deorbit can be up to 10% off.